All right, let's talk about probabilities of independent events. So these are events that are going to happen sequentially, or sometimes we call them compound events when we're talking about probability. So independent events are events that do not impact each other. They have no effect on one another. Let me give you a couple of examples of independent events, and then I'm going to give you some non-examples so you can compare them. And then what we're going to do today is focus on calculating the probability when events do not affect each other, so when they're independent. Okay, so here's an example of two independent events. I flip a coin and then flip the coin again. The coin has no memory. It doesn't know what happened in the first flip. That's not going to affect the second flip. Let's say spin a spinner and then roll a die. Those two events have no impact on each other. They are happening independently. Okay. Let's say I choose a card from a deck, see what it is, replace it, shuffle the deck, then choose another card. The cards have no memory. The two choices have no impact on each other. Here's an example of not an independent event. Let's say I'm taking a free throw in basketball. And when you take a free throw in basketball, you get two shots. Let's say I miss the first shot. That might impact the second shot because maybe I'm going to get more nervous that I'm going to make the second, not going to make the second one. Maybe my confidence is going to be reduced. Maybe I'm going to have higher chance of making the second one because I'm going to be more careful. But definitely the two shots will have the chance of impacting one another. Okay, let's say I'm picking random candies from a bag. And then I eat it. And then I pick another candy. The first pick will impact the second pick because I've eaten a candy now. So it's changed the number of candies in the bag. So it's going to change the probability. So those are non-examples. We're not going to deal with those today. We're only going to deal with independent events today. So there's a formula we can use for calculating the probability of compound independent events. So let's say we want to calculate the probability that event A happens. Maybe that's flipping a heads on a coin. And event B happens. So maybe it's flipping another heads on a coin. What you do is you just take the probability that event A happens and you multiply it with the probability that event B happens. So it's just probability of A times probability of B. This only works if the events are independent, meaning that they don't impact each other. Okay, so let's do some examples and see how this works. So let's say we have this deck of cards and they're shuffled up and they're flipped upside down. So we're going to pull two cards from this hand, but we're going to replace the first card before we pull the second. So the events are independent. They don't impact each other. Okay, so let's do the first one. It says both cards are even numbers. So that means what's the probability that we pull an even and then another even? Oops. Sorry, I'm just going to erase that because I spelled it wrong. So the way we do this, because they're independent, is we just get to multiply these probabilities together. It's the probability that we get an even times the probability that we get an even. So the probability that we get an even card is... So there's 1, 2, 3 even cards out of 5 total cards. So it's going to be 3 out of 5 times 3 out of 5. And just a quick reminder on how we multiply fractions. We just multiply straight across. So just 3 times 3 and 5 times 5. So it's going to give us 9 out of 25. That's the chances we pull 2 even cards when we're pulling from this particular deck. So again, we just multiplied probability of even times probability of even. Okay, let's do this one. sum is less than 7. Or sorry, the card is less than 7, and then the card is greater than 7. So the chances we get one that is less than 7 is only 1 out of 5. There's only one card that's less than 7. And the chances that we get something that's greater than 7, well, there's 3 cards that are greater than 7. So it's going to be 3 out of 5. And then we're going to just multiply these together. So 1 times 3 is 3. 5 times 5 is 25. So this is only going to happen 3 out of 25 times. Okay. 9 is pulled both times. So that's the same as probability of getting a 9 times the probability of getting a 9. So let's do those. 9. Chance of pulling a 9, well, there's only one 9 out of the 5 cards. So it's just 1 in 5 times 1 in 5, which is 1 in 25. That's not going to happen very often. Okay, neither is a 10. So the chance of not being a 10 is 4 out of 5 because there's 4 numbers here that are not 10s. And the chance it happens twice in a row is going to be just those 2 probabilities multiplied. So 16 out of 25. Okay. Now, let's look at how these would change if we did not replace the first card before pulling the next. So these aren't independent events, but we can still use multiplication as long as we change the percentages. Okay, so let's look at the first one. Probability we get even. So this time we're not replacing the first card, okay? So probability we pull an even. There are 3 cards that are even to start with. So it's going to be 3 out of 5. So that's the chance we pull an even on the first draw. Now let's say we drew the 6. That card is gone now. We did not replace it, right? Now on the second pull, there's only 4 cards left to pull from. And only 2 of them are even now. So it's only 2 out of 4. So now we can multiply these. So it's going to be 6 out of 20, and you can reduce that to be 3 out of 10. So see how the numbers changed? Because it's now out of 4 because you didn't replace the first card. So I would maybe pause the video here, see if you can do the other ones. And then I'll go over the answers now. So probability, we have less than 7 and then greater than 7. So there's 1 card out of 5 that is less than 7. Now there's only 4 cards left, but 3 of them are greater than 7. So it's going to be 3 out of 20. A 9 is pulled both times. So the chance you pull a 9 on the first one, this is kind of interesting, is 1 out of 5. But now that 9 is gone, you didn't replace it. So there's 0 cards left that are 9s now. So the chance you do this is 0 out of 20. The probability is 0. It's not going to happen. You can't. It's impossible to pull a 9 2 times if you don't replace the first card. Neither card is a 10, so there's 4 out of 5. And once you pull one of those away, there's now 4 cards left, and only 3 of them are not 10s. And you can reduce this one to get 3 out of 5. Okay, let's do the last question. This is one of my favorites because this is kind of a misconception that a lot of students have about the chances of kind of guessing on a multiple choice or a true-false quiz. Okay, so you have a quiz, but you forgot to study. There's 3 questions on it, and they're multiple choice. So the quiz looks something like this. You've got 3 questions. There's 4 choices per question. And you're just going to guess because you haven't studied. So you're going to guess randomly. What are the chances you get all correct? So you get 100% on this 3-question quiz. The chances are probably a lot lower than you think they are. So what we want to do, if we get them all right, that's the same as saying question 1 correct times the probability of getting question 2 correct times the probability of guessing question 3 correct, because all 3 of those things have to happen. So chances you get question 1 correct is 1 out of 4. Chances you get question 2 correct is 1 out of 4. 3 correct is 1 out of 4. So 1 times 1 times 1 is only one way that this can happen out of 4 times 4 times 4, 64. It's only going to happen in 1 out of 64 quizzes. If you convert that to a percentage, it's about 1.6%. That happens very rarely. And this quiz is only 3 questions. If you increase the number of questions to say like 9 or 10, it's almost impossible to get all of them right. It happens so rarely. Okay, but the probability of getting 0 on this quiz, all of them wrong, is quite high. So this would happen 3 out of 4 times 3 out of 4 times 3 out of 4, which is 27 out of 64 times, almost about 42% of the time this is going to happen. So almost half the time you're just going to get 0 on the quiz.